Welcome to this masterclass explainer. If you've been following along with basic blockchain tutorials, you've probably noticed a pretty massive gap. There's a big difference between writing a simple toy token and actually pushing code that handles real-world value. So today, we're moving way past basic syntax. We're going to learn how to build, break, and secure a production-ready smart contract. We need to start treating your code exactly like what it is, a financial vault.
Okay, so to stop writing vulnerable code, we really need to adopt this three-pillar framework. It focuses squarely on clean architecture, automated security testing, and EVM gas optimization. Because look, we aren't just trying to get the code to compile here. We are engineering it to survive in the highly adversarial environment of the blockchain, where, as you know, even a tiny vulnerability carries a massive financial price tag.
All right, let's kick things off with Section 1, the Developer Mental Model.
Stop teaching syntax. Teach security and EVM behavior. This is a huge point. Most Solidity tutorials fail you because they just teach simple syntax. But a true blockchain developer understands that deploying code is literally like dropping a transparent bank vault onto a public street. You absolutely must understand how the Ethereum virtual machine, the EVM, executes your code under the hood. And crucially, you have to anticipate exactly how attackers think.
Moving right along to Section 2, Building the Core Contract.
Let's start the build by looking at the core architecture and storage layout of a modern Solidity contract. Notice the difference here. A standard basic function leaves your contract wide open for anyone to call and manipulate. But by adding a simple modifier like OpenZeppelin's only owner, bam, you instantly restrict access to critical state variables. It's a fundamental architectural choice that dictates exactly who holds the keys to your system. And this brilliantly illustrates how modifiers act as a clean, highly visible way to handle permissions before your core contract logic even executes. You can see the only owner modifier explicitly checking that the message sender is indeed the owner, using a simple require statement. If they aren't, well, the execution stops dead in its tracks right there. It saves gas, and more importantly, it saves your protocol.
Next up, Section 3, the re-entrancy vulnerability.
Now, even with all the right permissions in place, our code might have a hidden, far more dangerous flaw. We're talking about re-entrancy. This is a devastating bug where an external, malicious contract basically hijacks the control flow of your protocol. By exploiting the order of operations, the attacker's contract repeatedly calls a withdrawal function, draining funds over and over and over again, all before your contract ever has a chance to update its internal balance sheet. And this isn't just academic theory, guys. These exact flaws have led to massive real-world financial devastation. We saw this in the infamous April 2020 Uniswap hack. We saw it during the Binance Smart Chain era with the DeFi Pie hack, and later on with the Popsicle finance bug. Millions of dollars literally vanished in an instant simply because developers failed to account for how the EVM processes state changes during external calls.
Which leads us perfectly into Section 4, Auditing Tools in Action.
To catch these crimson exploits before they ruin us, we absolutely have to introduce automated security testing and auditing tools into our daily workflow. Honestly, you just cannot rely on manual code reviews alone anymore. Looking at the developer ecosystem, Hardhat really dominates the landscape with its robust JavaScript and TypeScript base, commanding almost 23% of the space. Meanwhile, Truffle still holds a legacy share, and the Python-based Brownie framework commands a highly dedicated segment of the ecosystem. Ultimately, the tool you choose shapes how you test.
Let's compare the heavyweights for a second. Whether you prefer the massive TypeScript support, incredible testing speed, and local node environment of Hardhat, or maybe the Pythonic testing elegance of Brownie, utilizing Web3 Py and PyTest. The goal is exactly the same. Both of these frameworks allow you to write rigorous tests that will deliberately try to break your contract before you ever touch a mainnet deployment.
And if you're wondering if these tools are truly industry standard, just take a look at these top protocols. Top-tier platforms managing massive liquidity rely entirely on these exact frameworks. Maker, Curve Finance, Aave, Uniswap, they all use Hardhat, Brownie, and dApp tools to secure billions in locked value. So, if it's good enough to secure a billion-dollar liquidity pool, it's absolutely what you should be using in your local environment.
Moving right into Section 5, Securing with OpenZeppelin.
Okay, so now that our testing frameworks have actually caught the vulnerability, it's time for our verified green moment where we sanitize and secure the code. The crucial takeaway here is this four-step mitigation process. First, you identify the bug with your hard hat tests. Second, instead of trying to write custom security logic from scratch, which is always risky, you import OpenZuplin's heavily audited standard libraries. Third, you structure your code using the checks effects interactions pattern. This means always updating your internal state before sending out Ether. And finally, you rerun those tests to get that beautiful green pass. This is exactly how you systematically eliminate re-entrancy risks.
But we can't forget about EVM optimization and safety during execution. Before we finalize our deployment, remember this golden rule: always test the waters using a free call. A call is essentially a free dry run that estimates execution and debugs potential problems. You want to use this before you execute a costly send transaction which actually spends your Ether and modifies the blockchain state. It's really the smartest way to ensure you won't hit an expensive out-of-gas exception once you're live.
And finally, Section 6, Deployment and Final Takeaways.
With our code rigorously tested, heavily secured, and fully optimized for gas, we are finally ready to push our bulletproof infrastructure out into the real world. Using Hardhat or Brownie deployment scripts, we can quickly spin up a local node or push directly to Ethereum. Just looking at a typical console output here, you can verify your secure state right from the terminal. The framework handles all the heavy lifting, giving you transaction hashes, gas costs, and contract addresses instantly. It's incredibly satisfying.
Let's lock this in with a quick checklist to finalize your professional workflow. Number 1, always manage your private keys and environment variables securely in a .env file. Number 2, never invent your own cryptography or standard mechanics. Just rely on audited OpenZuplin contracts. Relentlessly test using Hardhat or Brownie. Always dry run your logic with a call before executing a send transaction. And finally, always verify your deployed source code on Etherscan so the entire community can trust it.
Which brings us to the ultimate realization for any blockchain engineer. As smart contract attacks become more sophisticated by the day, you really have to ask yourself, as you continue your journey in Web3, are you just writing a basic syntax exercise, or are you engineering a truly bulletproof financial vault? Keep testing, keep securing, and I'll catch you in the next explainer.